Okay, let's recap what we learned for the last 2 weeks. For the last 2 weeks, what we discussed is the baseband binary data transmission. And so far, we discussed transmit filter at the transmitter, also receive filter at the receiver. Also, we have a channel here. Okay? So we put these 3 blocks together and make a 1 block. And our goal is that to make these 3, make this red box to be a Nyquist channel. Right? In order to make a Nyquist channel, we need to make this kind of Nyquist channel in the time domain and frequency domain. So simply speaking, a Nyquist channel looks like we have a rectangular pulse in rectangular transfer function in the frequency domain, and in time domain it's like a sinc function. But what you see here is a continuous time, right? Sinc function is a continuous time. So based on this continuous time signal in time domain, now you're applying a sampling frequency. Okay, now you are doing sampling because we are discussing discrete time signals, right? Digital signals. So when you sample it, what you want to do is you are going to sample at the right position here, right? So since you are sampling here, 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 at the right position, now what's going to happen is you only have one value at right here at the right sample point, and on the neighboring sample point, you're going to have a 0. On the next sample, again, you draw a sinc function. So for that particular sample, again, you only have that particular sample value. All the other sample, you got a 0. Next sample again, next one again, right? So every sample you draw the sinc function, right? But since you are doing sampling at the right time, you only have one sample at right position. Now think about this way. Let's say you didn't get the right sampling frequency. Okay, you have a little bit off. In that case, let's say you need to do sampling here, 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 every 0 crossing point. That's the correct sampling. But let's say you sample it a little bit off here, here, here. Think about that way. Okay, if you do that kind of sampling, a little bit wrong, it's wrong sampling. Now what's happening is you have a right value here, but you're going to have a little bit of interference. Again, a little bit of interference, right? Little interference. Now on the next sample, you have another sinc function. Again, you have a little bit of interference. All of those remaining interference will be added with the next sinc and next sinc function, right? That's going to be interference. That's the ISI, intersymbol interference. We don't want that, right? What we want to do is that we want to sample it right position so that this pulse has no impact onto the neighboring samples. 0, right? 0, 0, 0. And next sample, again, you have a sinc, but you have a 0 sample on the following sample, right? That basically means that you have no ISI. Okay? That's a Nyquist channel. So you need to choose the right sampling here in order to make a perfect Nyquist sample, Nyquist channel. So that's our goal for this block. Now the problem is that this channel is random, and somehow it is unknown to us. So what we can do is that we can measure this channel impulse response and also transfer function. Based on that, now we work very hard to design transmit filter, receive filter put together, and hopefully we can make this whole thing to be Nyquist channel. But the transfer function has a different purpose. Transfer function is also called as a pulse shaping filter, and the reason of doing this pulse shaping filter is to shape your pulse so that you can make some good spectrum in the frequency domain, right? So what you want to do is that you want to make some spectrum like this. The raised cosine is one of the examples of pulse shaping, right? You want to make a nice frequency domain shaping. That way you can also reduce the interference on the neighboring samples, right? That's one of the purposes of this transmit filter or pulse shaping filter. But still, everything is not perfect. So you use some pulse shaping filter here, but the channel is always making your symbol like have a lot of deterioration. So this channel will change a lot of things of the symbol you transmit. You transmit symbol here, right? Once you transmit, it goes into the channel. This channel always creates intersymbol interference, phase rotation, everything, fading and everything. So because of that, you are going to get very wrong symbol, very weird symbol here. So what you need to do here at the receiver is equalization. Right? You need equalization here because of all of the intersymbol interference and all of those things by channel. So at the receiver, what you need to do is you need to have equalization. Okay? That's what you need at the receiver. So simply speaking, this equalizer is a filter, like this kind of filter. Simple filter. Okay? But this is not like low pass filter, high pass filter. Okay? Low pass filter is to pass the low frequency and block the high frequency. Okay? Some of the frequency pass, some other frequency block. That's what you want to do, high pass or low pass filter. But this filter, okay, this filter is to equalize transfer function. Remember that the just remember this one, right? We have some kind of channel, and this is what you transmit. You have a transmitter here, right? You have a transmitter. You have a receiver. This is a simple block diagram, right? You transmit something, transmit signal now goes into the channel. After channel, you receive it. Now what happens is this channel is not perfect, so you have some intersymbol interference. I'm drawing an impulse response. Let's say this is an impulse response of the channel. Now what happens is the receiver has a lot of intersymbol interference. Okay? So now what happened inside of the receiver is that you put this signal, received signal, into the equalizer. And this equalizer is a filter. And what you do in this equalizer is, this is a time domain impulse response of the channel. But when you look at this one in the frequency domain, the frequency transfer function of the channel always looks like this. This is a impulse response of the channel, so time response. This is a frequency response of the channel, right? Because if the time response is impulse, just one, the frequency is going to be flat, right? But this is not one. We have a multi-path. We have a multiple taps. So therefore, you have some fluctuation in the frequency, right? Now we have this signal comes in here. What happened in the equalizer is that change this one into, that's this one, right? After the equalizer, what you want to do is you want to make it flat. So change this into this way, equal. So that's an equalizer. So you are making equal. Okay, that's an equalizer. So how do you make it equal? Like this, right? Some of the frequency you suppress it, some of the frequency you raise it. Something like this, right? So you make it equal. Once you make it equal, transfer function in frequency, this is frequency, right? In frequency, if you make it flat, that is basically the same as in time domain, you have impulse, one impulse, right? This is what we want, right? Ideally speaking, this is Nyquist channel. Remember that? Yeah, Nyquist channel. What is a Nyquist channel? Nyquist channel we discussed is in the frequency domain, it's like this. In time domain, it's like a sync function. But if we choose the right sampling, here you have 1, 0, 0, 0, 0, 0, 0. This is a Nyquist sampling, right? Nyquist channel. So this actually is a Nyquist channel, same as Nyquist channel. You see here, this is like from minus negative to positive negative. Maybe you say this is different from this, right? But actually it's the same. Why? Because we have a pulse shaping filter here, right? At the transmitter, we have a pulse shaping. Once you have a pulse shaping filter, now you are transmitting, let's look at here, you are transmitting only your bandwidth. Your spectrum, your transmitted spectrum looks like this. So this one now goes into the channel. So make it accurate. This is actually your channel. So make it flat. That means this one. So this is what it transmitted here. Now this one goes into the channel. By the channel always have this impulse response or this transfer function. So this is what you receive. Same bandwidth. Okay, same bandwidth. And now this transfer function in the frequency goes into the equalizer. Equalizer make it equal like this. So this is what you get. This one actually same as this one in time. And this one exactly same as Nyquist channel. Okay? So this whole block, this whole thing, like a pulse shaping filter and channel, equalizer, combining these all together, pulse shaping, channel, equalizer, combining them all together, we want to make it as Nyquist channel like this or like this. That's eventually what we are doing. Okay? So once we make it this way, by combining these three blocks, now everything is perfect. If you get this output, here, that means perfect. Okay, perfect, everything perfect. What do you mean by perfect? Once you have this output here, that basically means that input to the pulse shaping filter is xn, and output from the equalizer is yn. Once you have this output here, that means your output of the equalizer is just the constant times of input. That means perfect. Okay? Perfect means this one. And in order to make this input-output relationship, we need to get this input, this time domain, frequency domain response of the whole thing. Okay? This is the whole story. Okay, that's the whole story. And look at here, this equations is talking about details of equalizer. How do you design the equalizer and how do you calculate the equalizer? Equalizer is a filter. So since this is a filter, you need to calculate the filter tap. Filter always looks like this, right? You have some number of taps. And each tap, you have some value, which we call as a filter coefficient. So you need to have a coefficient. So you need to calculate these things. Now, how do you calculate these filter taps? This is how to calculate. Right? This is how to calculate. So you multiply C. C is the input to the equalizer. Now the W is the equalizer itself, the filter. You multiply these two, then this is going to be the output of the filter or output of the equalizer. Why do we have this output? Because this output means this one, right? This one. So we want to make that, right? We want to make this output. So in order to make this output, we already know the input. We know this is going to be our output. That's what we want. We don't know yet is this one. This one we don't know. So by calculating this, how do you calculate this? This is a matrix. So you're calculating inverse matrix. Bring it here on the right side, right? Then you can calculate the filter coefficient. That's how to calculate the equalizer. Okay? And once you calculate all W values, you're going to use that one here. Okay? That's going to be filter. And then you're going to get this whole picture. Okay? So that's a whole story. Okay, that's what we discussed so far. Now what we're going to talk about today and next week, is a digital baseband modulation technique, right? Okay, so we heard the baseband, the digital bandpass. So we heard bandpass or baseband, passband. We heard a lot of those things, but And also we heard the pulse modulation and many things. So this digital bandpass modulation is, again, we are thinking about a transmitting over the air. Okay, when we start the digital communication, we talked about pulse modulation, right? Earlier we talked about PAM, pulse amplitude modulation, pulse width modulation. But all of those pulse modulation is not to transmit the air. Okay, that's not for transmitting in the air, right? That's only for the circuit or chip-to-chip communication or PCB and those things, right? That communication, pulse modulation is used on that scenario. This baseband, bandpass modulation is now transmitting over the air. Now, in the transmit over the air, we already learned AM, PM, FM in analog, right? In analog transmission, amplitude modulation, phase modulation, frequency modulation, those modulation technique is used to transmit over the air. These things is a digital version. See here, we see that the very same thing here. Amplitude shift keying, that's the same as amplitude modulation in analog, but this is digital. Now, phase shift keying, this is like a PM, phase modulation in analog. Frequency shift keying, that's the same as FM in analog. But all of these three are now digital communications, digital modulations. That's only difference. The concept is exactly the same. So you already learned AM, PM, FM. So same thing, it's same concept still there. Only thing is that this is a digital version. Okay, pretty much the same thing. So we have three of them, same as an analog. And right here, you also see that in the receiver, we have a coherent detection, non-coherent detection. We already learned these things, right? When you talk about analog, we already learned coherent detector. What was the coherent detector? Coherent means what? Phase of the transmitter, phase of the receiver should match. Okay? Transmitter, receiver, you are going to match the phase. That's a coherent detector, right? You use the same thing. In the digital, you still use the coherent detector. Phase should match. Okay, that's a coherent detector. But still, you can still use a non-coherent detector. What is a good example of non-coherent detector in analog? Costas receiver is still coherent because you match the phase, right? So what was the non-coherent? Amplitude, envelope detection. Yes, envelope detection is one good example of non-coherent detection. Okay, in digital communication, you can have a similar thing. We call it as energy detection, but same thing basically. So you can still do the non-coherent detection. Generally, this one is much better. Coherent detection have a better performance. But problem is a little bit more complex, right? More complex. But this is much better. And every digital communication system you use these days is all non-coherent. Only in a very simple case, sometimes you see non-coherent, but this is not much used. Pretty much every system you use coherent detection these days. Okay? So all of these words and concept is the same as analog. Okay? Everything you learn in analog still apply here. Okay, we already learned this carrier, right? This is a carrier. We already have this carrier earlier in analog, right? We use the same carrier. Why is that? Because we are using same channel, air. Okay? We transmit over the air. Analog, digital, doesn't matter. Because carrier is a function of the channel. If you use underwater, let's say you do a communication underwater, then you're going to use another carrier, like acoustic carrier. Okay? So the carrier typically is a function of the medium, function of the channel. It doesn't matter analog or digital. Okay? So that's why we use this carrier, because we, again, is transmitting over the air. Okay? So same carrier. You see these three here, but these three are actually same thing as the digital communication, digital modulation we discussed, but this is a simple version. This is the amplitude. Let's go back here. This is, we call that as ASK. Okay, now we are no longer, we are going to call that as amplitude shift keying. Okay, so from now on, we are going to call this one ASK, PSK, FSK. Okay, in analog, you heard AM, PM, FM. Same in digital, ASK, PSK, FSK. This ASK, we have a B in front of ASK. That means B means binary. Okay, so this is a binary ASK, binary PSK, binary FSK. So that means our information is a binary. What is binary? Like a 0 or 1, right? Two different information. That's a binary. Since we are talking about digital communication here, now everything is a bits, right? Everything is bits. So we transmit like a binary information using ASK modulation. This one, we transmit binary information using PSK, or this one, FSK. So that's the story. But the carrier we're going to use is same as the analog here, because we transmit over the air. Okay, what this basically means is now, since we are talking about digital communication, right, we are doing sampling, right? Sampling. When you do sampling, always you need to have a sampling frequency. For example, Fs. Okay, that's going to be your sampling frequency. Once you sample it, right? Once you do sampling, you're always going to have a bit duration or symbol duration. We're going to call that symbol bit duration as a TB. So what's the relationship between the sampling frequency and TB, bit duration? Let's say sampling frequency is 1 kilohertz. 1 kilohertz. What does that mean? That means you make it 1,000 samples a second, right? In 1 second, you make 1,000 samples. 1 second, like you are getting some signal like this. Within 1 second, you are sampling like this and make 1,000 samples. That's a sampling frequency of 1 kilohertz, right? So what's the bit duration? Every time you sample it, you make 1 bit. Okay? In that case, what's the bit duration? That's TB. TB is 1 millisecond. 1 over 1,000 second, right? Because you have 1,000 samples within 1 second. Of course, one sample has the duration of 1 millisecond. Of course, right? So this one and this one is the inverse, of course, right? Now this TB, that's the bit duration. Now let's think about the binary symbol here. When you do that, okay, then binary, okay, let's look at the binary for a second. Let's say binary information. What is a binary information? The information that you are transmitting is going to be only 0 or 1. That's a binary, right? 0 or 1. Then what about -1 or 1? Is it binary or not? It is binary. Then what about 2 or 5? It's binary. It doesn't matter, right? It doesn't matter what is the actual value. Binary means two different information. That's the binary. Maybe this is like a -1,000. This is 100. Doesn't matter. Okay, that's not important, right? We only have two different information. That's a binary. So 0, 1, 0, 1 is a simple, right? That's why we call the 0, 1, because that's a simple form. but it doesn't matter. So all of these things is binary. So since we are talking about binary here, now let me give you an example of binary data. So binary data, as an example, let's say I have 1 0 0 1 1 1 0 0. Let's say this is my data. Let's say. Then let me say that 1 means on, 0 means off. Okay? If you assume that, then what I do is this is what you get, right? 1 0 0 1 1 1 0 0. Something like this, right? Now that is a bit duration, TB. Again, this one, same. Every sample, every bit, you have a same duration, TB. Because we fix the sampling frequency, right? Sampling frequency does not change. So we sample it every time, every TB seconds. This is information now we have. And later, now what we're going to do is that we are going to multiply carrier. Remember in analog, right? In analog, we did the same thing. Now let me compare the analog. In analog, what happened was let's think about AM in analog modulation. You have a message, analog signal, right? Comes in and multiply the cosine carrier. I'm talking about DSB here, DSB. That's how you make transmitted signal ST, right? This is a DSB modulation. You have information, multiply the carrier CT, and then that's going to be ST. Now in ASK, this is a digital version. How to do that is this is what you get. Same thing, actually. What's the difference? Only difference is your message, because your message is now binary. In the earlier, in analog, your information was analog, something like this. But now in digital, your information looks like digital, like bits, 1 0 0 1. That kind of bits now comes in, and you're going to multiply the same carrier. That's going to be your output. So the only information looks like different. Everything else is same. So you're going to use this carrier. Okay, I'll talk about this one in a minute. Okay. So here is ASK, PSK, FSK. So remember the graph when you have AM, PM, FM. So this one actually looks like AM. Okay, almost same as AM, right? In the AM case, you also have different amplitude. Okay, if you have depending on the message, if the message has a small value, you have a small amplitude. If the message has a large value, you have a large amplitude. That was AM. Here, in ASK, same thing. Your information is 0. So 0, information 0 comes in here. That multiply with the cosine. What's going to be the output? 0. Because input is 0, you multiply cosine, output is 0. So you have 0. Whenever information is 0, you have 0. Now when you have a value 1, you have some output, which is carrier in this case. This is your carrier, right? So nothing, carrier, nothing, carrier, carrier, nothing, nothing, something like this, right? So that's your ASK. So when you look at this, what you can see is that the amplitude changes, right? Amplitude was 0, and some amplitude 0, some amplitude. That's ASK. So your information is in the amplitude. Same as in AM, in analog. This is a case of PSK. Now you see here, right? Our phase is changed. Okay, phase is changed. Okay, now let's take a look at the phase. What is the range of the phase? What is the minimum and maximum? Phase always can change from 0 to 2 pi, 360 degree. Okay? And since we are talking about binary information, we only have 2 different values. So this information and that information should have a different phase. So we need to make 2 different phases. Now the range is from 0 to 360 degree. And which 2 value would you choose? You're going to choose like a 0 and 180, right? 0 to 2 pi. That's the maximum phase. And you're going to pick the 2 different phases because we are talking about binary. So which 2 do you choose? One of them you choose 0 degree, and probably the other one you want to choose pi. Why is that?
Inverse.
Because this is the best choice because you're going to have a maximum distance between the 2 symbols, right? If you want to make if you pick 2 different phases, like a 0 and let's say 10 degree, like our range is from 0 to 360 degree, but if you pick 0 and 10 degree, that's a very bad choice, right? Because these 2 looks very close, and there are these many degree you are not going to use, right? This is a wrong way of choosing the degrees. So the best way is to make these 2 different information to be as much separated as possible. So you want to make it 0 and 180. That's the best choice. And 180 degree of phase means 180 degree phase rotation means what? 180 degree phase rotation basically means inverse of your sign, right? So let's see here. Think about cosine. We are using cosine as a carrier. 0 degree, here's a 0. You have a 0 degree, you have 1. 180 degree means you are in a -1. So always a 180 degree difference means that sine value will be negative. Positive becomes negative, negative becomes positive, right? Sine reversal. That's the phase rotation of 180 degree. So when you look at here, right, this basically means that whenever your information is 0, your phase rotation is 0 degree, 0 phase. But when you have 1, you have 180 degree phase. So that's why I see here is suddenly inverse, suddenly reverse the sign. It was like a cosine and suddenly minus cosine. Okay, a minus cosine. Again here it becomes plus cosine again and minus cosine again, something like this, right? Every time you see here, this is a discontinuous point here. Reverse change here again. Reverse the sign, right? That is actually, this is the point where phase changes. That's a phase rotation. And we call this one as a phase PSK. This is a PSK. This same thing happened earlier in the PM, phase modulation. You did the same thing. But in the analog phase modulation, the difference is that this phase changes was continuous. But in this case, it is binary. So we only have a 2 phase, 0 phase, 180 degree phase. We only have 2 phases. That's why you see sudden change, suddenly phase changes. That's the only difference. In analog, you didn't see this. Analog, it was like this cosine is getting faster, like a FM. Right? That's what you see earlier in the PM analog case. But in the digital case, the phase suddenly changes. So that's a PM. The last one is FM, the FSK, right? Frequency shift keying. In this case, right, frequency shift keying, depending on the information, you use a different frequency. Whenever you have a 0, you have F1 for frequency. Whenever you have a 1 in information, you use F2 frequency. So that's why in this case, 0, 0, you use a little bit slower frequency. Whenever you have a 1, a little bit faster. 0, a little bit slower, a little bit faster again, slower again, faster again. Something like this, right? You see the frequency is changing a little bit, right? That's the case of FSK. Out of these three different modulation, we have ASK, PSK, FSK. Same thing in analog version is AM, PM, FM. So in analog, which one was the most popular? In analog communication, FM was the most popular, right? Now you hear the FM radio, but you never heard about PM. Or maybe AM is a little bit used, but FM is much popular, right? That was analog. In digital communication, this is the most popular, PSK. Okay? That's the most popular. This one, analog and digital, it's not much used, right? What was the reason? What was the reason that AM was not very good in analog? Because of the noise. Okay? When you have a noise, AM is not a good choice. Or ASK, same, right? Your information is in the analog, is in the amplitude. That's not good because of the noise, right? So this is not that popular. You can still use, but not that good. In digital communication, PSK is the most popular one, PSK. Sometimes you can use FSK, sometimes, but this is not that much popular. This is always used, PSK. Okay? And some other cases, this one and this one is used as a combined together. Okay, we'll talk about that later. Okay, now let's take a look at one by one here. In this slide, we are looking at the binary ASK, BASK. So that is this one, okay, binary ASK. There are a couple of different ways of binary amplitude shift keying. One is on-off keying. We call it as on-off signal. Okay, what that means is when you have a 1, that means on. Whenever you have information off, that means nothing. Okay, so that's an on-off keying or on-off signaling. So as you see here, for binary symbol 1, you have some energy. Binary symbol 0, you have nothing. So that's exactly this one. That's what I draw here. Okay, this is a on-off signaling, like this one, on-off signaling. So this on-off signaling, like on-off. Okay, maybe I should talk about this one. So what is this? E sub B. Whenever you see E, that means energy. Whenever you see subscript B, that means bit. So that is a bit energy. E sub B is a bit energy. So every bit, every small bit has energy. So this is one bit, right? This is one bit. So this one bit has an energy. So this one bit has energy. How do you calculate the energy? So how to calculate energy is that this is the amplitude. So in order to get the energy, you need to do square, right? Because energy is different from amplitude. So you need to do square and do integration. And your integration is from here to here, because that's a bit duration. That's how to calculate the energy. So if your energy is E sub B, let's say, that's the energy in this bit. Same here, same here. This bit has also same energy. Every bit has the same energy, E bit. That's what we define as E sub B. This information now goes into the modulator. This is ASK modulator. Now we multiply the cosine into that. Let's say we have a coefficient A, okay, just a constant value A, and then you multiply, and you're gonna get the ST. We transmit this ST over the air. This ST now looks like this. So how do you get this? You multiply this value, right? This value right here. So that means this A is actually this. You multiply this carrier. Why do you multiply this carrier? Where do you get this from? Simply speaking, right? Let's think about a simple way. Let's say we have here, you see, this one, let's look at this one. This one you have a TB, EB, 2 times EB divided by TB, right? So that basically means and your BT. Root to EB, right? So that basically means that I was trying to get this one by this way, but let me do it this way. So what this equation basically tells you, simply speaking, this is not that important right now, but energy of the bit is EB. But when you calculate the ST, right? ST is transmitted over the air, and you now see the TB here, right? And you still see EB. The reason that you have a root square EB is because that ST, this is a ASK, so same as a AM. And remember in AM, your ST is message times CT, right? Same here. This is ST. This BT actually same as your message. This is your message. In this case, in the digital, they say BT. In the book says BT, but this one actually same as BT, empty. So your information is a carrier multiplied by this information. This is our information to transmit, like a 0, 1, 0, 1. So that's the one. So you are multiplying this BT into the carrier, and our carrier is this one. This is our carrier. This is our carrier. And this carrier multiplied by this one, BT, that's how you get this ST. Okay? This one times this. Then question is, now why do we get this? Right? Why do you get this in carrier? That's the question, right? Why do you get this in carrier? I mean, this one actually, okay, this one was not in the analog, right? In digital communication, we have this coefficient. And why do you have this in carrier? This is a carrier, right? So let's think about square of the carrier, square. Now, if you do square, right, then you're going to get 2 times TB, because it is a root square, so you square of that, then 2 divided by TB, and you have a cosine square. Now you think about integration. Okay, integration, then this whole thing, cosine square, becomes 1 over 2 because you do integration. Now these 2 cancel out. You are going to remain as a 1 over TB. Okay, why do you have a 1 over TB? That's because this one is a TB. And your energy, EB, is actually same as, if this one is alpha, if this is alpha, then alpha squared times TB. That's your EB. But you have in carrier, you have 1 over TB. This one cancels out. And that's alpha square. That's why alpha square, so what is alpha? Alpha is root square EB. So that's how you get this. Does it make it complex? Okay, well, if that's a complex, just simply remember that your energy, bit energy, 1 bit has energy this much. E sub b is a 1 bit energy, and you have 2 times 2 divided by TB in order to make average, in order to make EB as the average, and cosine carrier does not increase any power. You multiply the carrier, you are not trying to increase the power, right? You are not trying to increase the energy. So simply speaking, the reason that we multiply this is a normalization. Normalization, right? You have information comes in. You are multiplying carrier. That's your output, right? You have some energy. This is a bit. So each bit has an energy. Now you multiply carrier. Okay, you multiply carrier. And when you multiply carrier, you don't want to increase the energy, right? For example, if you have like a 2, let's say your carrier looks like this, 2 times cosine. In that case, the output, you are going to have a more energy, right? Because your carrier is big. It's like amplification, amplifying the signal. So you have a more energy. But that's not what you want. You want to have like the same energy still there here. You want to have a same energy, input output. Only thing you want to do is that you want to multiply the cosine without increasing the energy. That's why you want to multiply this. Try to make this one have a 1, output 1, the energy 1, right? So you want to leave it as same energy. That was the ASK, binary ASK. This one is a binary PSK. As I said, this is the most the common ones, right? PSK. So this PSK information is in the phase. Okay, your information is in the phase. So now this is a binary. We're going to pick only 2 different phases, right? One, you have a 0 degree. And the other one, you have a phase rotation of pi, which means 180 degree. So if you look at the cosine 2 pi fct plus pi, this one actually same as minus cosine. Think about that your cosine is shifted by 180 degree, right? It's going to be like a minus cosine, right? So this one actually same as minus cosine. So eventually, when you do the PSK, binary PSK, it's the same as you transmit cosine or you transmit minus cosine. Basically same as that. That's a binary PSK. Okay, that's what it is. This is a block diagram of binary PSK. Okay, if you remember all of these things, right? If you understand everything in this slide, like a block diagram, then you know everything about binary PSK, BPSK. We call that as a BPSK. Okay? First thing to remember is this one. This is what you want to remember. Every time we look at the phase shift keying, okay, Remember that phase shift keying is the most popular digital modulation. So every time you see the PSK, you will see constellation plot. This is called the constellation plot. Okay? So what is a constellation plot? Constellation plot is like an XY graph. X-axis is a cosine or real component. Real. Y-axis is imaginary. So which means that we are talking about complex value, like alpha plus A plus JB, something like that, right? We're talking about this one. Okay, so that's the constellation plot. And typically in the constellation plot, you will see a circle with a radius 1. That's what we call as a unit circle. Okay, you'll see unit circle in the constellation plot. And what this constellation plot shows you is the signal amplitude and phase. So every signal has amplitude and phase, right? So you're going to see amplitude and phase together in this constellation plot. What we are talking about here is a phase shift keying. So phase is the most important thing. Then constellation plot is showing phase. Okay. So how do you show the phase? Phase, okay, first thing, let's look at the amplitude. How do you know the amplitude here? Amplitude is measured by the distance from the origin. Here's the origin. And you see the distance. Let's say you have some signal here. Then this is the amplitude. If you have some signal here, this is the amplitude. Okay? So that's the distance. That's the amplitude. What about the phase? Phase is rotation from this axis. So for example, this signal, what's the phase? This is the phase. That's how much angle you have a rotation. That's the phase. What about this signal? This is a phase. Okay, that's a phase rotation. So every point you have, let's say here, you have amplitude, you have a phase rotation. That's the constellation plot. Pretty simple, right? That's a constellation plot you see here. Now let's take a look at binary PSK or BPSK. So in this constellation plot, we're going to plot the BPSK signal. Okay, BPSK signal. And BPSK, it is a binary signal, so we have only two information. And since this is a BPSK, a PSK, these two different signal information has a different phase. And as we already discussed, 2 means one have a 0 degree, the other has 180 degree. That's the best choice of a phase rotation, right? So one has a 0, the other has 180 degree. So 0 means you're going to have here, right? Your one symbol is on this axis. Only that way the phase is 0. The other symbol you have 180 degree. That means on the second symbol, the symbol should be on here somewhere, right? That's going to be your 180 degree. So simply speaking, one information is here, another information is there. So this is the symbol where you have a phase rotation of 180 degree. This is the symbol you have a phase rotation of 0 degree. And what is the amplitude? That's going to be root square EB. Why the amplitude is root square EB? That's because EB is your energy of your bit. And we are going to put the root square Because this is an amplitude, right? E sub b is energy. E sub b is the energy. So what is amplitude? Square of the energy is your amplitude, right? So that's why one symbol is root square EB. The other symbol is right here. What's the distance? This is again is a root square EB. But here it's 180 degree. So how do you say that? This is a minus root square EB. Like that, right? So these 2 points in constellation plot will give you binary PSK. So every time you hear BPSK, like a BPSK, BPSK is the most common and simple modulation in digital communication. Whenever you hear BPSK, you need to remember this picture. Okay? You're going to remember this picture. That's a BPSK. So, okay, now let's think about BPSK in practical systems and how it works. Originally in your message originally starts from 0 or 1. Okay? So let's say 0. You have a 0, 1, 0, 1, 1, 1, 0, 0, something like this, right? All of this bit sequence comes in here. Comes into here. Here we have a 0, 1, 1, 0, 0, 0, something like this, right? What happened inside this block? This is a transmitter. We call this a modulator, but this is a transmit side. Whenever you have the 0, 1, 0, 1 information, what happened here in the encoder is that 0, every 0 you get, you're going to change into this. Every 1 you get, you're going to change it to that. Okay? So you're going to get only your information input. Your input is 0 or 1 every time, right? Every time 0 or 1. So whenever you get 0, this is your output. Whenever you get 1, this is your output. So since we are using BPSK, your output is always this one or this one. That's your output of BPSK. Your input is 0, 1. 0 or 1. Your output is this one or this one. That's a BPSK, simply. We call this one as an antipodal signal. Antipodal means sign is reversed. That's antipodal. Why do we call that? Because when you look at the output, these two has the opposite the sign, right? This one is a plus, this one is a minus, but the amplitude is same. So that's the antipodal signal. Your amplitude is same, but one is positive, the other is a negative. That's antipodal. Okay? So that's your output here, BT. Okay? Your BT looks like this one or this one. Okay? After that, now inside the modulator, you are multiplying carrier. Once you multiply the carrier, you're going to get this signal. That's what you transmit over the air. So this is a signal you transmit over the air. Now when you look at the signal over the air, it's going to be this one or this one. Why is that? Because let's think about this way. Let's say you get 0. 0 comes in. Okay? You get 0, binary, right? Bit 0 comes in. Then by this block, you're going to map it into minus root square EB. So you're going to have a minus root square EB here. That minus root square EB is multiplied with this. What do you get? You're going to get this. That's what you transmit over the air. Same as 1, right? If you get 1, then right here, you get this value. That is multiplied with the carrier. You're going to get this output, this output. So every time you get like a 0, 1, 0, 1, you're going to transmit this one, this one, this one, this one, something like this, right? That's what you transmit over the air. And when you do that, right, 0, 1, 0, 1, then you transmit this one and this one, this one, this one. Now you see the same, this one and this one same, only the phase is different, right? 0, plus cosine minus cosine, plus cosine minus cosine, something like this, right? That's the signal you see here. That's this one, right? See here, like a minus minus plus plus minus plus plus, something like this, right? That's what you transmit over there. So this signal you see here is what you see right here. That's what you transmit over the air. That's BPSK signal. Now you transmit over the air. Here's the receiver. And this signal is received right here. And what happened after that at the receiver is multiply the same carrier. Okay? We did the same way in analog case, right? In analog, we also did the same thing. You multiply carrier again. After you multiply carrier, what did you do? You put it into low pass filter, right? Same thing in analog. Why? Because in the signal, the band pass signal, you have a cosine. So this signal now comes into the receiver. You are multiplying cosine again. Then after that, you are going to get cosine square, right? Cosine square now is multiply cosine square. You can change it into 1 plus cosine 2 times FC. Remember that? 2 times cosine 2 times FC. 2FC will be removed by low pass filter. Only the DC component will pass, right? And then you do a sample because we are talking about sampling the digital signal. You do sampling again and then put it into decision device. So that's the whole scenario of BPSK. Last thing that I want to mention is, what is this decision block? This is actually very complex block compared to others, but I'll give you a simple idea. This decision-making device is eventually making a decision. What is the decision in here? In this whole scenario, what is going to be eventually decision you want to make? 0 or 1? That's your decision. Because what you transmit is 0, 1. Eventually you transmit 0 or 1. So eventually you want to make a decision like 0 or 1. That's your decision. So how do you make a decision? Again, based on the constellation plot. So that's why this is important. Whenever you receive some signal here, right? Input to the decision, now in the receiver, you're going to draw the constellation plot. Okay? Because we know that at the transmitter, you use this constellation plot. So at the receiver, you're going to draw the same constellation plot and make a decision based on the constellation plot. Okay? So eventually, that's what you want to do. Okay?